Hey, greetings. Starting with homework today. Hey, Google, call my phone.
Got it. Your LG phone should be ringing now.
Alright, so I got a viewer. So, so it's the lecture course that we're doing because the lab hasn't come through yet. Here are yesterday's notes and yesterday's videos. Here's the syllabus. Oh, I'm still not, I guess I'm not connected to the chat, am I? I should be able to see it on my laptop, just not my phone, I guess. Late assignments will get half credit. All assignments are due by midnight. I mean, I didn't see. Maybe some Gatorade. Not sponsored. Why does it say that? Okay, so my chat's working. Oh, does anyone else feel like it's just such a shitty day? Describe the characteristics of sinusoidal functions. Determine if the function is leading or lagging. Convert between the time and frequency. Oh, hey, Evan. Are you streaming today? SpongeBob. Okay, I feel like I should take notes on some of this stuff. Hi, Emma. No day off today. Back at it tomorrow. Then day off Wednesday. Oh, okay. Interesting. Cool. I'm always missing pencils. Doing house chores, working on the screen though, Ah, here's a pencil. Again, not my favorite pencil, but does its job. I found in life that completing your work is always rewarded with more work. So hopefully you're doing stuff you love. This is not... I think I should zoom in that camera. I used to have it positioned a special way. I can zoom it in more. And then this is the one. And then I have to change. Yeah, I think that's pretty decent. I guess it doesn't save, like, cause I had to reconfigure video settings. Nice, yeah. I had to reconfigure the video settings to what I had adjusted them to prior. So that's a little annoying. I'm sure that there's a way to save it, but I'm just not like a specialist when it comes to OBS. Okay, so so let's see. I have videos. And okay, so I think I'm going to start by emailing my professor because I looked at the syllabus and I also looked at the online course material. Let's see, this is for circuits EET 2100 00. So it doesn't look like all the things are posted here, and I was talking to one of my other followers, and they use the system and said that like it's complicated and sometimes professors just don't upload everything, so I guess I have to like email him and make sure he puts in stuff like test solutions aren't up, assignments. See, I just have one test. What about quizzes? No quizzes. According to the syllabus, there's supposed to be a test due today, but that is not reflected. I think I'm going to ask the professor if there is a practice quiz, because that would be helpful. Alright, so Mr. Haddad. Oh, how's the audio level? Is my talking like decent compared to the music? Because I know it's gonna sound different to me. Yeah. Nice, Dank. Okay, so EET 2100. I think I emailed him about the syllabus already, though. Unless that was the other class and the other professor. Oh, no. Syllabus correction. Okay. How long ago did I send that last email? Sunday at 5. And today is Monday. He hasn't responded to me. That's not good. But maybe he's just gonna correct the syllabus. Because there were some dates that are wrong. I feel like I'm a TA helping with the administrative portion of this course. Like the syllabus says February. Like this is a summer course, so I don't know why February is on the syllabus. Okay, so EET quizzes. You always gotta send nice emails to professors because they work hard and they grade your homework. And so, yeah. Gotta see, what am I gonna say? Hi, Professor. I noticed on the syllabus it alluded to a quiz being due today. However, I have seen no quiz in Canvas that is due today. Well, I guess now that I'm writing that out, I mean, do you think he must know that the quiz isn't on the system? Because, like, he can't just, it's not like tomorrow he's gonna be like, how come no one did the May 31st quiz? I've seen a quiz in Canvas that is due today. Maybe I'll say I'm not complaining. Just want to express my confusion. Hope everything is okay. Let's see. So, on another note, I was wondering about the quiz due in or on June 20th. Is it possible that I can have a practice exam? Also, let me note, let's see. Also, how long is the quiz going to be? How many questions? Oh, no. Yeah, I gotta reword that. Is the quiz going to be how much time and how many questions will be on it? Thank you, Emma. Oh, I have a second viewer. I don't know who it is. Okay, so I must have had some communication from this professor. What did he last say about the quiz? Because he said something. He said something. The dad. Oh, there was a Zoom. Yeah. Okay, so I have one thing from him. Is there another Zoom meeting with this class? Upcoming meetings? No dates. No data. It's just a free-for-all in cyberspace. check the inbox. Favorite courses. This one. Okay, so the professor said, videos and test one. These videos are posted under modules. The test is posted under assignments. Okay, yes. This is good. So, oops. Okay, I'm almost ready to start watching videos again, or taking notes, or doing something like more like actual studying. Oh, I'm gonna close these other windows I don't need. Okay, close you out. Oh, my second viewer went away. Okay. Hi, Professor. No science syllabus and quiz being due. As you know, quizzes. Not complaining, just want to express. Hope everything is okay. Another note, I was wondering about the quiz due on June 20th. Is it possible that I can have a practice exam? I don't need it graded. It would just help me feel well to take the exam. I guess sometimes when I have multiple questions, I like them to be, this is like an old thing I would do, is number them or put them on bullet points. Because like maybe he'll respond in line. I don't know. I find with a lot of people, like, send them an email with more than one question, and they just don't respond to every question. And I don't do that to people. I don't know why people do that to me. But I don't know. So let's see. We have complex numbers and their conjugates. Actually, let's look at this. So I have 36 videos. Let's get a can I get a, let me get a calculator on the screen. Wait, what happened to my... Okay, what am I doing? Shit. Okay, so here we go. Okay, my second viewer is back. I don't know if that's like a new one or an old one, but I hope you're ready for some math. Okay, so Oh, was that my professor? No, that would be too good to be true. Okay, so I have 36. Why is that saying? No, I want to clear everything. I don't want to have the answer 0. Okay. So I have 36 videos, and it's like, yeah, like 26. Is that right? Well, I don't think I can study every day. I don't know. It would be nice to see a sample quiz, because then I would know what I do and don't know. Polar phaser. What is the polar phaser? Yeah, that's probably going to be a big thing. Yeah, I couldn't join that one because I was not around. Okay. So I guess last time I stopped around solving phaser part 1.
Here's another example that has capacitors and inductors. We have a current source with the value 4 cosine 100t minus 20 degrees. amp. It's a current source. It's an AC current source. That's what squiggly line is for. We have a resistor of 5 ohms. We have a capacitor of 1 millifarad. 1 millifarad. We have a resistor of 2 ohms here. And we have an inductor of 20 millihenry.
Henry's, yeah.
And the question, can you find the current through that 2 ohm resistor as a function of time? So I'm going to use phasor here. So my 3 steps. You have a problem in time domain right now. We want to solve it. So step number 1, convert to phasor. So let me convert this to phasor. The current source becomes a value 4 angle what? Negative 20. It's a minus, right? So let me convert this to phasor. The current source becomes a value 4 angle what? Negative 20. It's a minus, right? The resistor, notice I treat them with boxes even because I don't want you to worry about is it capacitor or inductor. The resistor doesn't change, the value of 5. The capacitor, negative J over omega C. Let's see what that number is. Negative J over omega C. Negative J omega is what? 100. And what is C? 1 milli, 0.001, so that's a negative 10 J, I think. This resistor is what? 2. No, I want to use boxes, not inductors. J omega L. J omega is 100. L is what? Which is 0.2, is it? 0.02 times 100, I'll make it what? 2J? And I'm looking for this current. So I convert everything to phasor. Step number 2, solve it in phasor. Well, let's look at that. To solve this in phasor, probably the quickest way, combine these guys into one. Parallel. The product over the sum. And these two are what? Serious. So when you look at that, there's my source. 4 angle negative 20. We'll come back, we'll think of a value for this, we'll see what that number should be. And we know that's going to be the sum of these two, which is what? 2 plus 2j. The question, what's this value? the product over the sum. The product, it's 5 times a negative 10j over the sum, which is 5 plus a negative 10j. Is that negative 50j on the top? Over 5 minus 10j. Let's see what...
Take a look at that. So this is showing that okay, so I don't know if my mouse is showing up, but at this circuit we have 5 and 10J are in parallel, and that is 5 and 10J, and so that's a well, yeah, that looks like a complex number. Let me just where'd my pencil go again? Oh yeah. So I think I'm going to try to do a breakdown of each of the terminologies in this study sheet. So we're dealing with complex numbers. Okay, so what is a complex number? Oops. Complex number. And then for my other note, okay. So what is a complex number? I love mathandsfun.com. So those are real numbers, imaginary numbers. Okay. Ah, a complex number is just the combination of a real number and an imaginary number. And imaginary numbers, when squared, give a negative result. Oh, that's a little more general than I thought. What is that readable? Okay, yeah, it is. What is that? I don't know why this is phrased like it's a controversial statement. Can a number be a combination of two numbers? Yeah. 4. 2 plus 2. 10. 5 plus 5. And, okay, so, oh, that's part of the complex. When squared, give a negative result. Normally this doesn't happen. When we square a positive number, we get a positive result. When we square a number, yes, I know. But just imagine such numbers exist because we want them. Talk about what the unit imaginary number, like. The unit imaginary number, like 1 for real numbers, is I, which is the square root of -1. Because when we square I, we get -1. I squared equals -1. 3i, 1.04i, -2.818i. So like anything pretty much with an I at the end is an imaginary number. I mean, literally. Okay, anything that includes an I, not even I at the end. Huh. Yep. And we keep that little I there to remind us we need to multiply by. Sure. Alright, this is probably worth writing down. Is that it? Yeah. That's so cool that you can see this. Okay, so we're gonna write down I equals -1. Ooh, that was kind of awful. As I'm doing this, I'm thinking about everybody that I know that works in tech. Some which make at least 6 figures. I don't think that any of them has like a bachelor's degree in engineering. Now, there is computer science, and I say the same thing still. It makes you wonder if I've jumped onto a pyramid scheme called undergraduate university. Okay, so And then we got I squared equals -1. I require more music. Oh shoot, I don't know why I put that up so loud. What if I did this? And then messing with the levels. Okay, so I think that if I cut the desktop audio to half, I can hear it very loud and my voice can be loud. But even still. Alright, this should be good. I hope so. Hi, second viewer. We're going over complex numbers today. Do you know what a complex number is? I wonder who my mystery second viewer is. It's too bad I can't see any names. Oops. Gotta switch it back. What is a complex number? So I, and then let me square I. Yeah. I worry about thinking that I'm monotone, and then I think of Lex Friedman, and he's pretty good at this YouTube stuff. He's pretty monotone. I is the notation I could have better handwriting for complex numbers. Okay, so we know what. Oh, shit. Nobody corrected me. I is the notation for imaginary. Oh my god, now I sound like one of my old professors when I made that no one's correcting me comment. Examples. Three I Oh man, what a day. Okay, so I think my pretend boyfriend David is in the chat. I don't know. Or watching, I should say, not in the chat. Chat is dead. But yeah, is that real? So a complex number is a Okay, so I think we understand what complex numbers are at this point, which is great. And I can do whatever I want with complex numbers as long as I have a calculator, which all engineering courses allow you to use a calculator on every assignment and quiz and test. So no problem with that. Where is my little... Where's my little... Oh, I think I was wrong. I don't think my friend David is in the chat. Sorry, watching. I have 3 people watching. I don't know who they are. Who are you people? Except for Evan. Y'all a bunch of lurkers. Lurking. Okay, so... Aha, here's my paper. Okay, so we understand what complex numbers are. Now, rectangular versus polar coordinates. Okay, what is a rectangular coordinate and what is a polar coordinate? Does anybody know? We will... ideally I should have some highlighters and shit. Okay, so let's just start with rectangular coordinates. Wait, what? I do not know how to do Snapchat. Rectangular coordinates or Cartesian coordinates. Who was talking to me about, who used the word Cartesian? Did I dream about it? I don't know. Alright, I gotta stop looking at my phone because I'm just about ready to get back to my work. Okay, so oh. Ah, so apparently some people that are watching, I don't think that they're... Well, I'm about to find out what's happening. Ah, that's too bad. I don't know. I can't keep looking at my phone. Let's see. Yeah, I gotta get back to my work. Rectangular coordinates. Cartesian coordinates come in the form xy. That's pretty standard. Polar coordinates come in, the other hand, the form r theta. So r usually means radius. X is the x-axis, y-axis. But then we have radius theta. So that's like a circular degree. Instead of moving out from the origin and using horizontal and vertical lines, we instead pick the angle theta, which is the direction, and then move out from a certain distance, r. Would anyone be mad if I made myself some hot cocoa? Let me see. How to do a Twitch countdown timer. Let's watch this educational content together.
What is up, guys? Welcome to another video in the Gaming Careers channel. Andy, and today we're going to be doing another OBS Studio tutorial. This time looking at how to add a countdown or count up timer into your stream. Now on screen now you can see the kind of thing that we're going to be creating in this tutorial, and of course I'll be talking through all the different settings so that you can customize it to look exactly as you want it to for your stream layout.
Too
so
much
you
blah
want one
blah.
of these countdown timers on your stream, well, typically they're used as a way of counting down to the start of your stream. So the idea is that you start streaming and you show this sort of countdown timer, and all your followers and viewers will get notification.
Yeah.
This allows all of your viewers and so the other way of stream, as well as the channels themselves. And what it does is it, similar to some of the Streamlabel software, it generates text files, which a software tool called Snaz, S-N-A-Z. And what So the tool that we're going to be using is a free software tool called Snaz, S-N-A-Z. And what it does is it, similar to some of the Streamlabel software, it generates text files which auto-update, and then OBS can read from those text files and display them to your stream. Now there are quite a few different online options for countdown timers that are popping up, sort of websites dedicated to creating a timer that you can then use OBS's browser source plugin to capture. But I wouldn't really recommend them for something like a countdown timer, because using browser source in OBS is a lot more of an intensive process for your CPU to do than just simply reading a text file. So it's going to be less intensive for your computer, and at the end of the day, streaming and recording, if you're doing both at the
Oh
same
yeah,
time,
why don't I just do
as well as
that?
playing
Screw
it.
this. I don't need to do that fancy Twitch crap. Wait, how do I... Okay. So... I'll say... I'm gonna do 2 minutes. Screw all that other bullshit. Who needs to bother with that? It's a little chilly in my room. Look, I'm like a vampire. I'm all super pale. I want hot cocoa. So we did start to learn a little bit about rectangular and Cartesian coordinates. Whoop.
What is
What is up? What is up? Please never let me turn into that. back with the mug. I think the music's a little too loud. That's interesting. Whoopsies. Oh, starting it over. Okay. Twitch, don't strike me for that Mexican music. I can't pin a tweet. Okay. Rectangular coordinates come in the form A Cartesian coordinate system in a plane is a coordinate system that specifies a Cartesian coordinate system in a plane is a coordinate system that specifically each point uniquely that specifies each point uniquely by a Cartesian coordinate system in a plane is a coordinate system that specifies each point uniquely by a pair of numerical coordinates which are assigned distances to the point from two fixed perpendicular oriented lines measured in the same unit of length. Oh yeah. I mean, rectangular coordinates are, it's a standard coordinate. let me get a picture of rectangular coordinates. Well, let's see what that GitHub was. I'm thinking of ending the stream. Ah, Cartesian coordinates are named after Descartes. This is like new for getting history of mathematics. Let's actually end let's see if there's a short documentary on calculus. Ooh, this is nice. A little 10-minute cartoon.
Have you ever wondered how calculus was discovered? It's an interesting story containing some of the greatest mathematicians of all time, and a little controversy too. The origins of calculus go way back more than 2,500 years to the ancient Greeks, where we begin our journey to the birth of calculus. In 400 BC, Greek mathematician Eudoxus used a method of exhaustion to find the areas and volumes of shapes. He discovered that the volume of a cone was 1/3 the volume of its corresponding cylinder. At around 240 BC, Archimedes developed this method of exhaustion further to prove that the area of a circle is equal to pi r squared. He did this by drawing regular polygons inside a circle until the regular polygon had so many sides it had practically become the circle itself. By coming up with the formula for the area of a circle, Archimedes invented a style of mathematics called heuristics. This was an approach to problem solving that's not quite perfect, but it's still practical and sufficient enough. Heuristics started to resemble early integral calculus, and Archimedes used the method of exhaustion to calculate further areas, such as the area under a parabola and the surface area and volume of a sphere. Archimedes was also the very first to find the tangent to a curve rather than just a circle, using a method that started to resemble differential calculus. When studying the spiral, known today as the Archimedes spiral, he separated the points of motion into two components, one radial and one circular motion. He added the two motions together, and by doing this was able to find the tangent to a curve. Moving on now from ancient mathematics and now fast forwarding to the 17th century. At this time, often called the century of the scientific revolution, many great mathematical ideas, formulas and proofs were discovered. Cavalieri developed a method of indivisibles in the 1630s, which was a more modern version of the method of exhaustion by Archimedes, and an early step towards integral calculus. Cavalieri's principle states that if we have two solids of equal height, sitting on the same plane with equal cross-sectional areas, as though we have sliced these solids up into flat cross-sections, then the volume of these two solids must be equal. Other European mathematicians in the 17th century, such as Isaac Barrow, René Descartes, Pierre de Fermat, Blaise Pascal, and John Wallis all began to discuss the idea of something called the derivative. But the two most notable mathematicians of this time, Isaac Newton and Gottfried Leibniz, were about to make one of the most incredible breakthroughs in mathematics of all time. In the mid-1600s, at the peak of this scientific revolution, a young man called Isaac Newton was living in Cambridge, England. As a teenager, he was removed from school, and his mother, widowed twice, tried to make a farmer out of him, but Newton hated farming. The master of King's School eventually convinced Newton's mother to send him back to school so he could complete his education, and it's just as well that he did. He quickly became a top-ranking student and stood out from his peers by building things such as sundials and windmills. In 1661, he began his studies at Trinity College, Cambridge. However, in 1667, Trinity College was closed due to the precautions from the plague. During this time, the 22-year-old Newton was trying to solve physics problems, but he needed to come up with some kind of dynamic mathematical system to help explain his physics problems of gravitation, motion, and the orbits of the planets. Foremost, he was a physicist, and he worked extensively on laws of motion and gravitation. But no mathematics yet existed to explain how an object falls, increasing in speed every split second. Newton also wanted to work out why the orbits of the planets were ellipses, and as a result he developed infinitesimal calculus, building on the work of European mathematicians such as René Descartes and Pierre de Fermat. By forcing a relationship between physical phenomena like the laws of motion, gravitation, and the orbits of the planets, he saw the need for the development of a whole new dynamic system of mathematics. So how did he come up with this dynamic mathematical system? The initial problem confronted by Newton was that it's easy enough to find the average gradient on a function using rise over run, such as the average speed on a distance time graph. However, what happens when the slope of the curve is always changing? A method didn't yet exist to give the exact slope on any point on a curve that was changing its rate multiple times. Newton started to realise that as the secant of a curve becomes smaller and smaller, the slope becomes an exact point, and we can draw a tangent at this point. We know that the tangent is a straight line that only touches the curve at one point, and so as the secant approaches zero to become the point on the curve, the calculation of the slope becomes closer and closer to the exact slope at this point. This is when Newton calculated something called the derivative or gradient function, which can accurately give the slope at any point on any function. Newton called this process of calculating the instantaneous rate of change the fluxion, and the changing y and x values the fluence, which is the differential calculus we use today. Once he had come up with the derivative function, or the gradient function, Newton established that it's then really easy to find the instantaneous rate of change on any curve at any point by just inserting a value for x. Newton then came up with the discovery that the opposite of differentiation is integration, and he named integration as the method of fluence. In his fundamental theorem of calculus, where Newton links integral and differential calculus, he states that differential and integral calculus are opposites or inverse operations, so that when you differentiate a function and then integrate it, the original function is retrieved. So what exactly is integral calculus? The integral of a curve is the formula for calculating the area bounded by the curve in the x-axis between two x points. The area under a velocity time graph, for example, would be the actual distance travelled. Integration can be achieved by breaking the area into infinitesimally thin rectangles and then adding up all the areas of all the rectangles to get the exact area under the curve. The thinner the rectangles are in their width, the more accurate the area under the curve would be, which eventually would approach the exact area. This is known as a limiting procedure, as the width of the rectangles approaches zero, in the same way that the length of the secant approached zero for differentiation. The development of mathematics by the Greeks up until this time was very static. However, calculus would allow for mathematicians and engineers to really make sense of motion and dynamic change in the world around us, such as the orbits of the planets and the motion of fluids. Newton was considered one of the most influential figures in history to this day, and in 1687 he published Principia Mathematica, the principles of natural philosophy which dominated the scientific view of the universe for the following 3 centuries. Moving on now to the second discoverer of calculus, Gottfried Leibniz. Gottfried Leibniz, born in Germany in 1646, was son to a professor of moral philosophy. He was lucky enough to inherit his father's personal library, who unfortunately died when he was only 6 years old. His father's library enabled him to study a wide variety of advanced philosophical and theological works not available in general schoolwork. He was only 18 when he graduated with a Master's in Philosophy, and after only 1 year of legal studies, he was awarded a Bachelor of Law. After meeting mathematician and friend Christian Huygens, he convinced Leibniz to dedicate time to the study of mathematics, and so in 1674 Leibniz began working on calculus. His approach to calculus was from a metaphysical point of view. He reasoned that the integral is the sum of the ordinates for infinitesimal intervals and the incisor, so the sum of infinite rectangles. From these definitions, he quickly identified the relationship of integration with differentiation, and he realized the potential to form a whole new system of mathematics. In 1684, he published his work on the theory of calculus, which included differential and integral calculus completely independently of Isaac Newton. As Newton hadn't published anything on calculus yet, a controversy arose as to who discovered calculus first. Eventually, Newton was credited as the first discoverer, and Leibniz was credited with the first published work. Over the years, they have been both accepted as independent discoverers of calculus. It was Leibniz who thoughtfully used superior notation to Newton, which is the notation used today in modern calculus. If we compare the calculus of Newton and Leibniz, the descriptive terms to describe change by both mathematicians was essentially very different. For Leibniz, change was the difference ranging over a sequence of infinitely close values called infinitesimals. These are the basic ingredient in the infinitesimal calculus developed by Leibniz. Infinitesimals for Leibniz were the small quantities such as the tiny rectangles and the tiny gradient values of the secant eventually approaching zero. They are so small, in fact, that there isn't any way of measuring them. Later on, mathematicians would describe this as a limit. The rise of calculus by Newton and Leibniz in the 17th century was such a unique and significant moment in mathematics. It was a whole new system and form of maths to help describe our dynamic universe. The benefits of using calculus to model any system of change or motion today is virtually unlimited in any field, such as medicine and economics, and is not restricted to physics only. We can appreciate Newton and Leibniz for pushing civilization forward in such a dramatic way in the 17th century by connecting the physical universe of motion and change with mathematics.
Alright, Maths with Lisa, that was pretty awesome. I feel like one of those teachers that pulled in the AV cart and just left the classroom and made the class watch a VHS tape. Oh my goodness. Well, that was somewhat productive. Well, yeah, who knows? I think I'll probably be on again later. Definitely be on tomorrow. Definitely have a lot of studying to do. Okay, so yeah, again, I'm gonna shout out Maths with Lisa. Criminally undersubscribed. Not even 4K subscribers. You got some good views there, but it's an old video. History of calculus, I mean, that's a timeless, that's like evergreen content. Look at this. Look at this channel.
Have you ever wondered how calculus was discovered? It's an
It's her
interesting
leading video.
story containing some of the greatest mathematicians of all time.
She sounds like Tibby's, but her name is Lisa. Oh, I love the golden ratio. We gotta see this.
Mathematics, art, architecture and music are traditionally taught as separate disciplines. However, did you know that they are intricately linked from great antiquity to modern times through a mathematical phenomenon? Mathematics, art, architecture and music are the application of human consciousness striving to express oneself through a physical or metaphysical reality. Aesthetically pleasing art, music and architecture are generally grounded in a mathematical phenomenon known as the golden ratio or divine proportion, sometimes referred to as sacred geometry. This golden ratio was defined initially by the ancient Greeks and was manifested in art and architecture and is still prominent today. We could even say that the golden ratio is the formula of beauty itself. The golden ratio is considered sacred due to its relationship with nature and the miraculous construction of the universe and the human body. We can observe this mathematical phenomenon in nature through plants, flowers and animals, the human body, the structure of genetic code, movement of the solar system's planets, and in the physics of high-energy particles. Well-known works of beauty that adhere to this divine proportion and hence produce magnificent masterpieces include Khufu's Pyramid of Egypt, the Parthenon in Athens, the Mona Lisa, and even in the captivating music of Beethoven, Chopin, and Mozart. Ancient Greek philosopher Plato, who lived during the 4th century BC, perceived that the universe itself abides by the law of harmonic division. Plato maintained that the goal of aesthetics is to peer deeply into nature, to employ the sacred proportions at work in her beautifully divine but simple order. Mathematically speaking, what exactly is this divine proportion known as the golden ratio, and how does it actually underlie aesthetically pleasing art, architecture and music? The golden ratio is an irrational number equal to 1 plus root 5 over 2, or approximately 1.618, and is represented by the Greek symbol phi. Recent mathematical history of the golden ratio can be linked directly to the work of Leonardo Fibonacci, an Italian mathematician, and his discovery of the Fibonacci sequence. The sequence begins with a 0, 1, and adding the two preceding numbers to get consecutive numbers in the sequence, we have 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 3 is 8, and so on. When we place each of these numbers of the Fibonacci sequence over their previous number, we get closer and closer to the golden ratio itself, 1.618. So let's see how phi geometry works in terms of the logarithmic Fibonacci golden spiral. Writing down the Fibonacci code, we have 0, 1, 1, 2, 3, 5, 8, 13, and so on. First, construct two 1 by 1 squares next to each other. Then, underneath a 2 by 2 square, to the left a 3 by 3 square, then above a 5 by 5 square, and finally an 8 by 8 square to the right. This is known as the golden rectangle. Then, beginning in the first square, draw an arc like so, making sure to pass through each of the vertex of each square. And here we have the golden spiral, known as the Fibonacci logarithmic spiral, that underlies beauty in the world around us.
Perfect.
The golden ratio manifests in the human body. The human body and all its parts, including the human face and even our teeth, are all based on the principle of the golden ratio. The 3 bones, for example, of each of your fingers are in a golden relationship. The wrist divides the hand and forearm into the golden ratio, and the human head is embedded within a golden rectangle with eyes at its midpoint. The mouth and nose are placed at golden sections of the distance between the eyes and the bottom of the chin. We can also see the divine proportion at work in plant leaves, stems, flower heads and petals, animals, weather patterns, and even in the structure of our DNA. The Parthenon, created in ancient Greece, is considered one of the greatest monuments of ancient Greek architecture. The main cause of the Parthenon's beauty is the exquisite harmony of its parts, based on the golden ratio. On analysis of the proportion of the building reveals that the main facade fits into a single golden ratio. On analysis of the ground plan, this reveals 2 reciprocal golden rectangles, and the interior chamber is also in golden proportion. The Mona Lisa, the well-known portrait of a woman with a coy smile and considered one of the greatest artistic masterpieces of all time, is embedded within golden rectangles. And through Vitruvian Man, Leonardo da Vinci shows the perfection of the human body in all divine proportion. Further works of artistic harmony and perfection can be seen in the masterpieces of The Last Supper, The Annunciation, and many more. The structure of both rhythm and harmony is also based on the golden ratio. The most pleasing harmonic intervals are the octave, 2:1, the fifth.
I would just like to note that whenever I create art, I am always thinking of the golden ratio. I wonder if I can. I wonder if I can show that in my most recent painting. Yeah.
Proportion. The Mona Lisa, the well-known portrait of a woman with a coy smile and considered one of the greatest artistic masterpieces of all time, is embedded within golden rectangles. And through Vitruvian Man, Leonardo da Vinci shows the perfection of the human body in all divine proportion. Further works of artistic harmony and perfection can be seen in the masterpieces of The Last Supper, The Annunciation, and many more. The structure of both rhythm and harmony is also based on the golden ratio. The most pleasing harmonic intervals are the octave, 2:1, the fifth, 3:5, and the major and minor 6, so 5:3, and 8:5. The piano itself consists of Fibonacci numbers with 8 white keys and 5 black keys in a ratio of 2:3. Russian musicologist Sabanev discovered in 1925 that the golden ratio appears in 97% of Beethoven's music, 97% of Haydn's music, almost 100% of Chopin's etudes, and 91% of Mozart's music. Looking outside to the macrocosm, the divine proportion also underlies our solar system and is often referred to as Aphrodite's golden kiss. Venus draws a beautiful 5-fold rosette around us every 8 years. 8 years on Earth is equivalent to 13 Venusian years. The Fibonacci numbers 13 to 8 to 5 here appear to connect to time and space. The relative mean orbits of Earth and Mercury are close to phi squared to 1, which is the same ratio as the size of the planets themselves to each other. The two largest planets, Jupiter and Saturn, also produce a perfect golden proportion from Earth. The synodic measures of time and space relate 1 to phi with 99.99% accuracy. If we line up Earth, Jupiter and Saturn, 1 year and 12.85 days later, the
Just
Earth
a little
is
bit more to
exactly
go.
between Saturn and the Sun. 20.79 days later, the Earth is exactly between the Sun and Jupiter, corresponding to the golden ratio. Given all the expressions of human consciousness through architecture, art, and music to create masterpieces of beauty and perfection, it truly seems that the mathematical ratio of phi, this golden ratio, is the mathematical code that underlies aesthetically pleasing beauty in the world around us, even in the code of the planets' orbits, their sizes, and motion in space and in time. Can we therefore say that there really is a secret mathematical code that underlies all creation of our magnificently beautiful universe and the expression of all human consciousness? Please share your thoughts in the comments below. Thanks for watching.
Oh, shoot. What was the next video they were gonna recommend? The golden ratio and Fibonacci numbers, fact versus fiction. No, thank you. Oh. Stanford. Ooh, it's Stanford. Okay. Bye. bye everybody. I'll be back tomorrow.